Okay. Thanks all for waking up this early and coming to see this talk. So the talk is about it's mostly the research that I did at my university. So I'm a PhD student at the University of Leuven in Belgium, and there I do research on security and privacy on the web, which is like a broad thing. But mainly my current focus is on side channel attacks in the web and in the browser, as I will be talking about today. So the concept of timing attacks is that they're a type of side channel attack, which means that it's not a direct attack like a SQL injection or something, but you try to infer information based on observations that you make from the environment. And well, these attacks are definitely not new. They've been known for decades, but it was mainly applied in cryptography. And there it was used to retrieve cryptographic keys or retrieve the message that was sent, the encrypted message that was sent, or to exploit secure connections. So for instance, I think most of you have heard about this Lucky 13 attack. It's also a type of timing attack. So the concept of timing attacks is pretty simple. First, you perform an action, which can be pretty much anything. It's of course based, the action that you do or make is of course based on the system that you're gonna attack. Then you measure the time from a starting point until the end. So that's something that you observe. And then you compare or analyze this timing measurement with some other timing measurements or just its absolute value. And then, you can exploit it. So some time ago, I came up with this new type of timing attack called the drunkenness timing attack. So in the drunkenness timing attack, you try to determine whether a certain person is drunk or not. So to do this, you first perform an action. So you slap the person in the face, and then you measure the time it takes from the starting point, so the slap in the face, until that person slaps you back. And if he slaps you back quite quickly, you can assume that he's not drunk. And if it's a long time, the person is drunk. But of course, in my research, I like to do experiments. So that's what I did. So I have this test subject who wanted to remain anonymous, but that didn't happen. So it's Matthias Berens. So I went to him and I was wondering, it was like in the middle of the day, and I was wondering whether he was drunk. So I performed the drunkenness timing attack. So I went to him and I slapped him in the face. And so that's when I start my timer. So you see he falls down and quite quickly he slaps me back. So it takes about 3 seconds before he slaps me back. So is he drunk? Well, probably not. But of course, that's just one measurement that we took. So yeah, in order to make sure that this time attack actually works, we need to do another timing measurement. And there, preferably, Matthias would be drunk. So then I gave him some nice Belgian beers. And after a few minutes, because he can't really hold his liquor, he was drunk. So I knew he was drunk, so I performed the timing attack again. So I go to him, and I slap him in the face. And then again, I start my timer. And now you see he has trouble getting up. So it takes quite a while. In the end, he slaps me back. So it's like 8 seconds. So again, the question, is Matthias drunk? Well, yes, and that's because the second timing measurement was significantly higher than the first timing measurement. So basically, that's how timing attacks work. With the drunkenness timing attack, the response time of the user or the victim relates to the person's drunkenness. And the same goes for recovering a cryptographic key. So there you measure the time it takes to execute something, and the time it takes is related to whether a certain bit of the key or the message is 1 or 0. The same thing goes for the Lucky 13 attack. So there you measure the time it takes until you receive a TLS error, and that gives you some information about whether the padding of the encrypted thing was correct, and knowing that allows you to retrieve the message that was sent. And then there are the web-based time attacks, which will be the main focus of today. So these web-based time attacks, they're also not new. They've been known for a very long time, so since 2000. And to give you an idea how long this is, so in 1995, cookies were first introduced. So 5 years after cookies were introduced, and well, they weren't widely used for some years after that, timing attacks had already been discovered. And then a bit later on, there were some more advanced attacks, like this nice thing by Paul Stone, where he could read out the value of a certain pixel in an iframe by adding SVG and CSS things to make the GPU rendering time take a different time based on the color of the pixel. And in the same year, Eduardo Vela wrote this nice blog post about a timing attack where input of the attacker is compared with a certain secret, and the time it takes to compare this, so it's the JavaScript execution time. It's related to the secret. So that allows you to extract information about a secret. And then you have they were, I think, first introduced in the academic world by Bortz and Bonnet. So they introduced the concept of direct timing attack and cross-site timing attack. So a direct timing attack, I will show an example of this. So here you have your attacker and your server that's going to be attacked, and the attacker will try to brute force the password of the Batman user. And to do this, he will send a post request and measure how long it takes until he receives an error. But with the username he puts Batman, which matches here. But for the password he enters something like AAA. But because the first letter doesn't match the first letter of the password, the server will very early respond with an error. So that allows the attacker to know that most likely A is not the first character of the password. So then he tries again with BAA. Now you see that the first letter matched, so the server compared the second character, which didn't match, so then an error was still returned, but now the attacker learned that B was most likely a correct guess because the timing was higher than before. By repeating this process, the attacker can try to brute force the password of the user. Of course, these things uh, only work in well, a very optimal setup, which is most of the times not the case for the attacker. So there's many limitations regarding these direct timing attacks. So one of the major issues is that you have to deal with irregularities on the network. So any jitter or congestion will mess up the timing measurements and will require the attacker to either make more measurements or just don't let him succeed in his attack. Also, the concurrent users that are using the service may influence the timing measurements because the load on the server will vary because of, well, if there's more users, the load will be higher, and so on. But some smart people came up with solutions for these attackers. So the main thing is that the closer you get to the victim server, well, the more precise your timing measurements can be. And well, in the cloud architecture, this can go to quite extreme forms. So you can try to make sure that your VM gets hosted on the same physical machine, and that allows you to do some cache attacks. And well, it also allows you to use very precise timing methods, like in the order of microseconds or even less. And if you then use some additional statistical tests, many attacks will succeed. But well, unfortunately, it would take a very long time to explain all this, and it's not really the focus of this presentation. So I will just recommend that you read about these things because they're really interesting. And I'll move on to the main topic of this talk, namely cross-site timing attacks. So these type of timing attacks are quite different from the direct timing attacks, because with the cross-site timing attacks, the request is no longer sent by the attacker, but here the attacker makes the victim send the request. And because the web was developed in such a wonderful way, all requests to third-party content will have cookie attached to them. So this means that the response that the user will get based on the request that was sent will be based on the state of that user. So for instance, if a user is logged in, he will see a dashboard if you request the root of the domain, and otherwise it will say that you're not logged in and you need to log in to see something. So then when you're logged in, the response will be large, and when you're not logged in, the response will be small. And then the attacker can measure the response time, so the time it takes to download the resource with JavaScript. So basically, you can load an image, set the source, and then start this timer. And when the image sends this on error event, the attacker can stop his timer because, well, typically the attacker is not interested in images, but rather HTML pages, and these are not valid images. So that's why you listen on error event. And so these attacks, the main goal of them is to violate the same origin policy. And just because it's so important, I will briefly zoom into the same origin policy. So it's one of the main security principles that exist on the web. And basically it says that a certain origin, so for instance attacker.com, cannot read anything from example.com, so from an other origin. So, well, it's not just the content that should be secret, but also the length of resources should be secret because, because the responses are based on the state of the user, and if the length is impacted by this, the attacker can learn things about the state of the user. Well, and this contains a lot of private information, as I will show later on. So I'll give a brief overview of how this attack would work. So here you have a social network consisting of two groups. So you have the Batman group and the Joker group. And here you have the victim. And this victim is browsing to a non-malicious website, for instance, google.com. And google.com has this malicious advertiser. Well, it wouldn't make sense that it's google.com because Google is an advertiser. But anyway, let's say this is New York Times, and New York Times has a malicious advertiser. And well, this malicious advertiser, he can execute JavaScript, but only in the maliciousAdvertiser.com domain. So he can't read out any information from this social network. And this advertiser will try to determine whether this user belongs to the Batman group or the Joker group, because obviously the advertisements that would be shown to the user will depend on which group he belongs to. So what the advertiser does is he makes the user initiate a request to the Batman resource, and because the user is part of the Batman group, because he's Robin, the response will be rather big. So it will take around 4 seconds. Then he does the same thing, but with the Joker group. So he requests the Joker resource. But as you can see, the response that's returned is rather small. So the time it will take to download this resource is also much smaller. So the attacker measures that it's around 2 seconds. So that's a lot less than the 4 seconds that he saw before. So that allows this malicious advertiser to determine that the user is from the Batman group. But of course, these things only work in ideal situations, which never occur in the wild. Because, well, in the wild, a request might look like this. So it moves over the internet, has some congestion. So as you can see, the timing measurement of the attacker now for the Joker group, it's 6 seconds, which was larger than it was for the Batman group. So yeah, this prevents the attacker from learning anything because he can't know for sure that this response time was for the Joker group, and it would always be smaller than for the Batman group. So there's, well, these timing attacks have several limitations. So there's first the network irregularities, which were similar as with the direct timing attacks, but in this case they are worse because the attacker can't control on which network the user is. So if he's on a bad wireless network, then the network timings will contain a lot of jitter. Then there's gzip compression, so that makes that the difference in response size is a lot smaller, which makes it much harder to detect that there's a difference. And so one of the things that an attacker can do if the timing measurements aren't always correct or there's jitter on the timing measurements is to take a lot of timing measurements and then do something like take the average. but in this case, the attacker will need a round trip for every measurement that he takes. And if there's some kind of rate limiting on the service, his attack simply won't work. So that's where the browser-based timing attacks come in. So these are a new type of timing attack, which try to overcome all of the limitations, or at least most of the limitations of the classic cross-site timing attacks. So the goal here is to start your timing measurement only after a resource has been downloaded, and by doing so, you don't have any jitter or any irregularities of the network that could impact your timing measurement. Another thing is that these browser-based timing attacks are much more accurate, which allows you to determine with more certainty which of two resources is the bigger one. And for some of the timing attacks that I will explain later, a resource only needs to be downloaded once, and once it's downloaded, you can obtain a lot of measurements in a very short time interval. So this is what the browser-based timing attacks would look like. So again, you make the request with the response, but you see that only after the response has been received, you start your timing measurement, and you measure the time it takes to process this resource instead of download this resource. So there's three types of processing that you can measure in the browser. So first is to try to parse a certain resource in a specific format. So for instance, by trying to parse an HTML document as a video, and if you manage to measure the time it takes to process this, so the processing time of the CPU, you will learn an estimate of the size of the resource. And the same goes for storing or retrieving a certain response from the cache, or putting it into the cache. So I will show a very basic time the most basic one, where you measure the time it takes to parse a certain resource as a video. So first you create a video element and you add two event listeners. So the first event listener is on the suspend event, and interestingly, this event will fire as soon as the download of the video is complete. So that's when you start your timing measurement. And because the time it takes to parse this element this resource as a video is rather small, it's best to use the high performance resource timing, so the window.performance.now. And you know that a resource has stopped parsing as soon as the error event fires. So that's when you stop your measurement, and then you can simply set the source of the video to the thing you want to know the size of, and you measure the time, and then that's all you need. So there's also another trick that you can do, and that's to use application cache. And that's so there you can first put this resource that you want to know the size of in the application cache. So then it gets stored on the disk. So then every time you set the source of a video element, it will take it from the cache instead of making a request to the network. So that allows you to do these timing measurements very quickly. So another type of timing attack in the browser is the cache storing timing attack. So there you will measure the time it takes to have this response object and put it into the cache. So you make the request object. So these things are using the service worker related APIs. So you have your request object with the URL you want to know the size of, some options which make sure that the cookies are attached to this request, and then some bogus requests. So first you fetch the resource, and once it's downloaded, you know that you can start your timer, and then you simply put it into the cache with the cache API. So this allows you to put any resource into the cache, which I think is a pretty strange thing security-wise. But anyway, and so once it's put into the cache, you can stop your timer, and so the difference here will allow you to infer some information about the size of the resource, because a larger resource will take a longer time to put into the cache. So how well do these attacks work? So it appears that they work pretty nice. So we did some measurements where we tried to determine how long it would take on average to differentiate between two resources where the difference of the resource size is on the x-axis. So as you can see, for the classic timing attacks, it takes like 9 seconds to determine a difference between file size for files that are 15 kilobytes different. So it still works, but these attacks were executed on our university network, which is relatively stable. So the measurements that we here obtained were in the favor of these classic timing attacks. But it's also interesting to point out that here, for where the difference in file size was 40 kilobytes, you can see that the attacker didn't manage to perform his timing attack. And most likely that was due to some kind of network irregularity that that happened when we executed that experiment. Now, when we look at the browser-based timing attacks, so the green, blue, and purple, you can see that they perform much better than the classic timing attacks. So even when the difference in file size is just 5 kilobytes, the worst timing attack still manages to differentiate between file sizes in less than 5 seconds. And when you look at the best performing timing attack, so the cache plus video parsing, so when you put the resource into the application cache and then do this video parsing attack, you can see that in less than a second you can differentiate between files that are only 5 kilobytes different in file size. So I will be showing a short demonstration now. And here I will focus mainly on Facebook. So Facebook has this functionality where, as a Facebook page, you can create a post and you can limit the visibility of this post. So you can make sure that the people that can see your post are from a certain location, or are all men or women, or are of a certain age. So for instance, people that are 26 can see this post, and when you're not 26, you can't see this post. And you get, so when you try to request it, and you're not allowed to view it, then you get this short error message saying that you can't view it because you're not in the the scope of the post. So in the demonstration, I will try to discover the age of a user. So this is any user visiting any website. So you could go to NewYorkTimes.com, where there's a malicious advertiser, or he could go to cutekittens.com and get his age exposed to the administrators of Cute Kittens, and so on. So the attack requires some preparation by the attacker. So the attacker first creates a number of Facebook posts, which are each targeted to users of a certain age. So as you saw before, you could limit the posts to a certain range of ages. So the attacker first creates a post that's visible to people of the age 13 to 22, 23 to 32, and so on. And then he will try to determine the range of the age the user is in. And that's because otherwise the attacker would need to do a lot more requests. So here you do some kind of, well, not really binary search, but something similar. And then, when attacking the victim, the attacker makes the victim fetch the corresponding resources, so the posts that were made, then obtain timing measurements for them, and then try to determine the range of age the user is in regarding the value of the timing measurements. And then in the third step, you will try to determine the exact age of the user by just repeating this process again. So here you will see a lot of boxes, and the boxes are just box plots with the timing measurements. So here you can see that here it says start downloading resources. So that's the first step. So the attacker downloads the resources corresponding to these things. So this is a post targeted to people of the age 13 to 22, 23 to 32, and so on. So it takes a while to download the resources, and then we will start obtaining timing measurements. So after, actually less than 10 seconds, or with some certainty, around 11 seconds, you can see that the timing measurements for the resource of users in the age of 23 to 32 is significantly higher than the rest of the timing measurements. So that allows the attacker to know that the victim is of the age between 23 and 32. So that's 10 different ages that he can be. So then again, he does the same attack, but then for the specific age. And you can see already that for the age 26, the timing measurements are again significantly higher than for all the other ages. So in less than 30 seconds, the attacker is able to determine the age of the user. Of course, that was just an attack that we launched against Facebook. Actually, there's a lot of, many more attacks that can be done by using these browser-based timing attacks. So on LinkedIn, for instance, it's possible to retrieve information about the connections of a certain user that's on a website. With Twitter, it's possible to determine which users the user is following, or in an extreme case, even try to determine the identity of the user. For Google, we found that it was possible to to browse into your search history. So any search term that you enter in Google gets saved by Google, and then later on you can search it. But of course, if you can search it, an attacker can also search it. So it allows them to know things about what you searched for. On Amazon, it's the same thing, but with your shopping history. And well, on tech discovered by someone else, allows you to search. Well, so on Gmail you have this search box where you can put something in, and as an attacker you can make the same request and then figure out how many responses were returned. And that allows the attacker to basically search into your inbox. These are just things that we looked at. So I think I spent like 15 minutes for each one to to come up with one of these attacks. So there's many more, because there's many more web services, and because these attacks, they exist by design of the web, most of them are vulnerable. Because these attacks are quite frightening, I think, it's best to try to come up with some kind of mitigation. Unfortunately, these are not as easy neither on the client side as on the server side, but especially on the client side, it's very hard to mitigate these attacks. And that's because the attacks are there by the design of the browser and the web in general. A very simplistic way of trying to mitigate these attacks would be to reduce the resolution of the timer. But unfortunately, that wouldn't work, because if you make the attacks a bit more intelligent, the resolution of 1 millisecond is already sufficient. So for instance, for the video parsing, you could simply parse a video multiple times in a row, and then a resolution of 1 millisecond would already suffice. A promising solution might be to disable third-party cookies. So when you're on NewYorkTimes.com and you make a request to Facebook.com, if the cookies are not attached to that request, the response that will be returned will not be based on the state of the user. So that way, the attacker will not be able to learn anything about knowing the size of that response. So that's something that you can do on the client side. So there's also the same site attribute on cookies, which need to be implemented by the server side. So the main goal of these same site cookies is to prevent things like cross-site request forgery, and the way it works is that it sort of also disables third-party cookies, but again, it requires an implementation effort by the website that is going to be attacked, and because there's so many websites, it's unlikely that all of them will implement this. So I've mentioned before that the cause of these attacks is related to cross-site request forgery, because in cross-site request forgery, the cookies are also attached to the request, and that allows the attacker to make some state changes at the at the website for the user. So if you can prevent illegitimate cross-origin requests, so for instance with a CSRF token, these attacks would be prevented as well. But here it's not only the post requests, but also the GET requests, and putting a CSRF token on every request, it might just be a lot of overkill. So basically, the security of browsers regarding these time attacks, it's not ideal, and it will likely remain bad. So we even discovered some new type of attacks, which we will be disclosing. So me and a colleague will be disclosing these attacks this summer. And these attacks allow you to determine the exact response size instead of an estimate. But the good thing is that it's possible for browsers to mitigate at least one of these two attacks. But unfortunately, browsers tend to, or browser vendors or standards people tend to take quite a long time, at least in my experience, to try to fix these issues. So to conclude, so I've presented this new type of browser-based timing attacks, where we measure the time it takes to process a resource. So that happens after the resource has been downloaded, which makes it the attacks are much faster and more robust than the classic timing attacks. And one of the major issues is that these side channels, so these timing side channels, they exist by the design of the web and the browser. So it's unlikely that these timing attacks will go away. And another issue is that many major popular web applications are vulnerable. So we're definitely not there yet regarding a mitigation. So it will be interesting to see what the future will bring, and whether attackers or malicious people will start using these attacks or not. We will see. So if you have any questions, feel free to ask. Okay. There's no questions, and thank you for listening.